Hello, I'm Dr. Taran Huffman. I'm the Senior Photonics Engineer at GenXComm. And at GenXComm, we use advanced RF and photonic techniques for the next generation of wireless communication, networking, and position tracking and location services. To that end, we've developed an ultra-low loss photonic platform with unparalleled performance compared to available commercial photonics. And this platform is directly applicable to navigation, most specifically to integrated gyroscopes, to reduce size, weight, and cost while still retaining high sensitivity and other advantages that come with photonic gyroscopes.
Photonic gyroscopes detect rotation using the Sagnac effect. We create a circular photonic path or coil and set counter-propagating beams around it. In the absence of rotation, these two beams experience the same path and there is no phase difference between them. In the presence of rotation, these two beams experience a phase difference which can be measured, and from that phase difference, the rotation can be deduced, allowing photonic rotational sensing. Fiber optic gyroscopes can reach truly impressive rotational sensitivities, are rad hard, and can function under high acceleration. They suffer from significant size, weight, and cost. Integrated photonic circuits can reduce the size, weight, and cost of photonic gyroscopes while still maintaining their advantages. Shown here is a typical GenXComm photonic chip, 21 by 25 millimeters in size. The performance of the gyroscope primarily depends on the area enclosed by the coil, the length of the coil, and the remaining energy in the two counter-propagating light beams. As a consequence, higher propagation losses reduce the maximum coil length and sensitivity. Shown on the left are two simulated coils and their sensitivities versus length. The blue line indicates a higher loss coil with 6 dB per meter of loss, and the green line a lower loss coil with 1 dB per meter of loss. Initially, both sensitivities increase as the coil length is increased. However, eventually, the sensitivity of the higher loss coil fails as the lower loss coil still increases. The lower loss coil optimum length has roughly 4 times the sensitivity of the higher loss optimum length. This is critical because integrated coils, in their effort to reduce size, will typically enclose smaller areas. This means low propagation loss is absolutely paramount to maintain performance of photonic gyroscopes. GenXComm has developed an ultra-low loss photonic platform, shown here on the left. We utilize high aspect ratio silicon nitride cores clad in SiO2. We have titanium nitride heaters and aluminum electrical paths to create heating switches as well as other active components. Typical propagation loss from this platform is 1 to 2 dB per meter. Other commercially available photonic platforms have higher than 45 dB per meter of loss. This process has been developed in university cleanrooms with some steps performed by external vendors, typically material depositions. This entire process is compatible with the CMOS foundry, which would enable extremely low manufacturing costs. These integrated photonic gyroscopes, utilizing GenXComm's low-loss propagation, can enable navigation and tracking in GPS-denied or unreliable environments with reduced size, weight, and cost. GenXComm was founded in 2016 by Sriram Vishwanath and Hardik Jain at the University of Texas in Austin. We're backed by Intel Capital, Azure Capital, and BMW I Ventures, among others. We have more than 40 employees in Austin, Phoenix, and California. Our goal is to leverage photonics and discrete RF for the next generation of wireless communication, networking, and position and tracking and location services.